Hi everyone. Can you please confirm if my screen is visible to us? Good enough. So wait, let me add a new plain text file here or notes. And in last session we covered fill functions. Okay, fine. So we will start with little bit of functions that was left out. And basically the only part that is left out is continued. So last topic of this is basically function overloading. Okay. So what does this mean? It means that functions will have same name but different parameters. Okay. It can be either different number of parameters. Again, one function takes one parameter, second one takes three, third one takes four, something like that. Or it can be different data types of parameters. As in, both versions take same number of parameters, but one is taking a vector, another one is taking an array, third one is probably taking a string, that sort of stuff. Okay, so it kind of works like this. Let us define a function here. So let me say int foo and the return a plus b, and we can probably print something int foo int comma int was called, and then we can have probably another function with same name, but say we are taking float instead of integers. So return a plus b, and we just copy it and print it, and that float was called. Okay. So if I call it like say 5 and 3, and then I call 2.1, 1.2. Okay, it says but okay, so it says that it is too ambiguous. Okay, it can go both ways. So wait, let me change it. Include string, and then delete string is, instead of taking two floats, I am going to take two strings. Oh, and here I can say std string, comma std string is called. Okay, and then here I can pass some string. Hello from world. Okay. Okay, so now I build it. Now I run it. Obviously, the function name is same. I am calling foo here and here both. But for first case, it is getting here this one because the parameters are integer and this is basically the only match. And for string, this is the only match. So this automatically goes here. Now, one can ask what happens if we have same number of parameters, same data types of the parameters, just the different return type. So that is not allowed. The return type is not used to resolve ambiguity, right? For example, in this case, we are not doing anything with return value. So there is no way to figure out which type of return value we were expecting and use that to resolve the function. So this return type does not matter. Only thing that matters is what parameters are here, what is their order, their data types, their total number of arguments, that sort of stuff. And even then, if there is any possibility of ambiguity, then we have to basically specify specifically that, okay, we are trying to pass this parameter as this particular data type. For example, if I have yet another function trying to add one short, one long, so that will be ambiguous because if I'm just saying 5 or 3, it can fit in short, it can fit in int, it can fit in long, all three. So that will be ambiguous. So that is also basically a no-no in C++ as far as possible. So this is what is called basically function overloading. We are using exact same name and we are redefining the same function to do things slightly differently depending upon what sort of parameters are available. Okay, and we will revisit this again in context of object-oriented programming. It will be, I think, either this lecture or next lecture. Okay, so this is where our function topic basically ends, and now we come to the next topic, that is file IO. And when we say that we are dealing with file IO, there are multiple things. For example, we will be dealing with directories, we will be dealing with files, okay, and the common operations will be create, we can rename, we can delete, we can possibly move it from one location to some other location, okay. We can read some metadata, for example, what is the file size, or maybe who is the owner of this particular file, or what sort of file is it? Is it a normal file, or it is some sort of a special file like a device, block device, character device, that sort of stuff. Okay. So there are two things here. This is basically split in two parts, and split in two parts. Part one is file system itself. So the file system library basically deals with the view of file system, as in your directories, your file names, file paths, directory traversal, recursive traversal, non-recursive traversal, okay, the file metadata, that sort of stuff. And then the second part is file. So this one deals with reading from file or writing to file. Okay, and this is where this part basically ends. You either are reading from file or are writing into file. This one deals with file system, does not do read from read write on files themselves. Okay, so directories, renaming, moving, deleting, that sort of stuff will basically be part of this. Before this file system library came to C++, this was actually part of Boost. It was lifted from Boost with slight modifications and merged into C++ standard library. And before this came into standard, the only way to do this sort of thing was either use Boost or you have to deal with platform specific APIs directly. So those APIs would be different on Windows, different on Linux, different on Mac, and possibly different on BSD. So if you want to support multiple operating systems, you either involve some library or deal with platform specific APIs on your own. Now it is part of C++ itself, so we don't really have to think about platform-specific APIs. We can just write the code in standard C++, compile it anywhere, and this will, for most part, work pretty much anywhere. Now, there will be some parts of this file system which will be more applicable to Unix family of operating system, like it will make sense on Mac OS, Linux, but those parts may not make perfect sense on, say, on Windows. But apart from that, the rest of the stuff is pretty much straightforward. Okay, so let me remove this. And for that, I will include this file system. And our first operation will be, okay, so we will start with file system, and our first case will be create directory. Okay, so what do we do for that? We use this hash include this file system library, and then we create a path, and the path will be std file system path directory path, and we can put some name here, example directory, and then we can use create directory std file system create directory path, and this is pretty much all that is needed. So we build this, and to run this, I need to go to the server because this is not going to provide any output. Okay, what is the path? The path is this one. So terminal cd this one. Okay, we have lecture 4, and right now there is no example directory. So I run this lecture 4, and then I do this, and now I see this example directory. Okay. Now it is possible that this may fail for whatever reason. Okay, and if you want to check whether this actually succeeded or not, you can use something like this. Says India else build it again, and okay, there is no directory. So I run this, it says success. I run it again, it says fail, because this directory already exists, so it cannot really create this directory. Okay. Similarly, I can specify some path like this, and if I build it now, it basically fails. because this example directory does not really exist in current directory, and we are trying to create a directory within that directory. Okay, so now if we want to handle this particular case, we don't really want it to terminate directly here. We want to handle this. So what we can do, we can deal with error code. So for that, we can file system. Okay, is that error code? Error code EC, and then we can specify this error code here, and what it will do, it will give us some sort of error code. Okay, and in that case, here we can put and we can print ec dot message to see what is failing. And now it says no such file or directory, and it is not abruptly terminating itself. So this is how we can handle these sort of cases. Now, if suppose I want to create directories like this, nested directory within a directory. So one approach is that I create the topmost directory first. If it does not exist, then create the second level of directory, then third level of directory, so on and so forth. Or I can basically create all of them in one shot. And for that, what I will need to do, okay, so what I will do, I will basically create directory, and I will put it here so that we have at least something to compare with. Okay, then we have create nested directories. Okay, and I will call it from here. Oh wait, it is this one. And now what I will do, I will do this one, and std file system create directories and specify path here. Okay, I build this again. There is no this example directory. So what I will do, I will just run this lecture 4. It works. Example directory is there, and then I can do this example directory. That foo directory is also here, and obviously that foo directory is going to be blank because we did not really create anything there. Okay, now okay, so we created a directory. We create nested directories, and now we come to removing directories. Okay, so for that again, we will create another function. Remove directory. And we will copy it here. And then we will do file system remove directory path. Okay, so here what I will do, create nested directory, and then from here I will call this remove directory. So it creates one, and no, okay. What I will do, I will just disable this. The directory is already here, and if I build and run this, the directory lower one should be deleted. Okay. So if I run this, I have that example directory, but within that example directory, this foo part is missing because it has been deleted. So what I will do, dir -p example directory foo, I will create this again, and I will remove that /foo part here, build it again, and run it again. And again, it says that it can't remove it because this directory, this one is not really empty, it contains something. So for that, what we can do, we can use another function to remove everything. And then we can do std file system, remove all directory path, and we do this here. Okay, so here we have our folder intact. We build this again, and then we run it again, and now the example directory with all its contents is basically gone. So removing an empty directory, in a directory with all its contents. Now we come to basically listing directory contents, okay, and listing directory contents. So basically there is some folder, and we want to see what other files or folders which are present in that directory. So for that we have this std file system path path. For that, what we can do, we can use the current directory for listing, and then we can use something called directory iterator. So it is std file system directory iterator, and then we gave it a path. Okay, and then what we want to do, we want to iterate over this. Okay, so what we can do, we can do auto entry, and we can basically print whatever is present here. Entry dot path, and it's a new line. Okay, so we remove this, and we call this function from here. And basically run it again. And it basically prints everything that is present here. Okay, whether it is file, whether it is folder, does not really matter. Whatever is present within that directory, all that will be printed one by one here. So we have done listing part. Then there is a possibility that we may end up having folders which themselves may have some other stuff. For example, we have these two folders here, CMake files and testing. So let us see if this contains, yes, this contains some stuff. Similarly, this folder contains some stuff. Okay. Now we want to iterate recursively, as in not only we want to see this, we also want to go in all those folders and iterate over them as well to see what is there. Okay. So one option is that we iterate like this, then we somehow find out which one of these entries are directories, and then we iterate over them, find other directories, iterate over them, so on and so forth. Or we can use a recursive iterator. So that will be listing directory contents recursively, or that we can create a calendar function. Recursive. And just like previous case, we can iterate over this. Std file system recursive directory iterator, and send to the path. This directory recursive, build it again. We run this, and now we see that it has printed a lot of stuff. And if you see here, there are entries which are directories. Then within those directories, there are some other directories which contain some other directories. So basically everything on every single path gets printed here. Okay. So instead of doing all that, looping ourselves and doing all the testing, whether it is file, directory, something else, we can just use a recursive iterator and we still end up getting all the file path. Okay, any questions so far? Anyone got any questions? Okay. So where was I? Yeah, recursive iterator. This part is done. Now we come to creating a temporary directory. Okay. And next one is creating a temporary directory. Maybe you want to store some data or just for some time and you don't really want it to persist for future. Maybe you want to cache some stuff as an intermediate stuff, whatever. you probably want a temporary path. Okay. So there are ways to do this. So void create temp directory. Okay, we will create a temporary file. And what we want to do, we want to create a directory. So std file system path the directory std file system temporary directory path, and then my tmp dir. Okay. So you see this one, temporary directory path. This will basically give you whatever intended temporary path for your particular platform happens to be. So for example, on platforms similar to Linux, it will be /tmp most of the time. On Windows, it will probably go somewhere in app data temp directory. On some other platform, it may point to some other location depending upon how things are on that particular platform. So instead of trying to figure out on which platform you are running and what is the basically designated temporary directory area for that particular platform or particular user happens to be, you don't have to do any of that. You just use this particular function and all that stuff is automatically taken care of by this runtime thing. Now you see that instead of using the usual ways to append the strings, we are not doing that. We are using a slash. That is your typical file path separator on most of the platforms which are not Windows. Okay, Windows is a special snowflake which uses backward slash, but other platforms use forward slash. So the same forward slash is used here as well. And this will basically make whole thing a proper path, which we will end up getting here. So we have our temporary directory, and then we need to create the directory. So std file system create directory, and so directory is created. And then we want to create a temporary file name. Okay. So we want to create a temporary file name. So std file system path tmp file is equal to tmp directory slash, and then here we can path my file.txt. So we can do this as usual. And then probably we can create a file at this particular path, and for that we will have to go to this one. So okay, fstream, where is this particular function again? Okay, so std of stream, we will cover this part in some time, what exactly this thing means. So file, so we basically open that file, and then we basically put some data, file close, and the file is created. Okay, so create file will be explained later what exactly is happening here. Okay, so we do this and then we call the function here, create temporary file, we remove this, it's build, and lecture 4. Okay, so what I will do, I will on/tmp. We don't have this my underscore tmp underscore dir. Okay, so now I run this and do lstmp again, and here you see that this is created here, even though I did not really specify that /tmp part specifically. That is being picked up by this because this is running on a Linux platform, and Linux platform /tmp is the temporary location. So my directory has appeared here directly. So if I do my tmp-dir, I have my temporary file with the name that I specified here. And if I try to read this, I see whatever stuff I have put here, it has appeared here. So this is how we basically create temporary files. Okay, now this is mostly about directories, and then we come to doing some file system stuff on files. So we come to copy files and wide copy files. So what we will do, we will basically copy this file system path. This is going to be the source file, and we also need a destination path. Destination where we want to copy it. Okay, so copy.txt. So we have both paths with us right now. So what we will do, we will copy this. So std file system copy resource destination, and that should basically work. Copy files. Okay, so if I do ls, here we have only one copy, and after running this, we should have another copy present here. So fingers crossed, and the file has been copied. You can see exact same size. Okay, and as usual, you can read that and confirm that the contents are actually the same. See, it has the exact same copy. Now, what happens if I run it again? And this basically fails. It says cannot copy file exist, yada yada yada, and then it aborts again. We don't really want that. Okay, so I gave you one method where you can take the error code, this one. So this is one way that you can specify the error code parameter, take the error code and do this if else thing. Or if it feels kind of yucky to you because you are coming from some other language which has really nice exception handling. So for that you can do something like this. Std exception, And instead of doing it bluntly like this, you can use try std file system error. So, std file system error, stdcl error dot what, and you can print something else here. And build this again. So now if I run this again, it says that file system error cannot copy file, but it will not magically abort itself. It will do something else if I wanted to do. Okay, so there are both ways. You can either use this if error code fancy you, or if you are a person who does not like this and you are someone who are more comfortable with this try catch statements, so you can use that as well. Both versions are available. Use whatever feels better with you. So we copied a file and now we want to copy some files, possibly recursively. Okay, so copy files and copy files recursively, as in copy directory, basically. Okay, and for that, what we will do, void copy directory. So what we will do, we will again start with some source and destination paths. And instead of files, we will have folders this time. So file system path source equal to, okay. ls/tmp/my tmp directory. So suppose I want to copy this and I want to copy destination into directory copy. Okay. Now what I want to do, I want to copy the folder. So this time we have to slight variation of that. So std file system copy source destination std file system copy options recursive. So basically what I am saying here, that this is the source, this is the destination, and copy this recursively. So basically read everything from here, everything, and then copy everything within here. Okay, and just like this, we can have that try as part here as well. Catch std file system error, and basically we can copy this here. Okay, so we want copy directory build, and we run it. And now we should see whether we are seeing the second copy. So if I do ls/tmp, my tmp directory, I see this. If I do this, I see the copy of that. So basically directories are copied. Then we can similarly rename files. Okay, any questions so far? Okay, there are a bunch of questions. Okay, do we have some kind of file path join function in a standard library that takes care of different types of paths and backslashes for us, like relative path, absolute path, and resolution, other edge cases? So if you want to combine paths, I think we did it somewhere here. So here, you see this? This is how we can combine paths. There is no need to involve another function. You can simply type this slash and then next part of path, and then you can type slash, then next part, then again slash, next part, so on and so forth. So you can use this path separator directly. Okay. So here, if you have some absolute path or maybe even relative path, you can specify the next chunk here. That will work. Okay, can you repeat line number 57? Do we need post underscore path? Line number 57. Wait, where exactly do you see this line number 57? Is this a declaration of another function? So I'm not sure what your question is. What is more idiomatic, generally accepted standard practice? That is try catch usually preferred more. Now it is 59. Okay, line number 59. And the question is, do we need post underscore path? I'm not sure what is the question here. If you can rephrase the question, that will be very helpful. Okay, so question from Gaurav, what is the more idiomatic? Okay, so the thing is that different libraries will have at times different way of doing things. So you will see some libraries which are heavy on try catch. So if you are using that, you will have to stick to try catch. Okay, then there will be libraries which are heavy on error code. So if you are using them, you will be using that error code stuff. Okay, then there will be libraries which will do the error handling in more like C style, where the output parameter has to be passed by reference where you want to capture the output, and they will be returning some sort of error code in their return values, and you have to check and interpret that pretty much everywhere. So it basically boils down to what sort of library you are using. For this standard C++ library, the stuff that we are covering, you can basically pick whatever style that suits you and then stick to that style. So ideally, if you are using that error code way, use it everywhere. Okay, or if you are using this try catch stuff, that exception handling, stick to it, do it everywhere. Don't unnecessarily mix multiple styles in one place. Be consistent, whether you are using error code, whether you are using exceptions. And again, there is no more idiomatic or more generally preferred or more correct way of doing this. This is kind of left to your personal taste and whatever libraries you are using. Okay, it will do we need my temp directory. Okay, yeah. So basically, we are basically creating the complete path. This is first part, and then we want to create this directory within this. So to create the complete path, we are using this operator here. Okay, so where are we now? Okay, we want to rename files. Okay, so again we need old name and new name. Okay, what are the paths here? Okay, let us suppose that okay, what I will do here, make file, and I will copy it as test file. So now we want to rename file. History, system, old name equal to test file, file system path new name equal to new file, or rather this one. Okay, then we can rename it as to the file system, rename old, rename to new. Okay, and we build this. We have this test file here, and I run this again. It's a file. Oh shit. Okay, I didn't call it here. Rename file. And this test file is renamed to this new file. Okay, now we come to create symlinks. Now this is something that will work on Linux, BSD, Mac OS. I'm not really sure whether symlink is a thing on Windows or not. So not really sure whether this symlink part will work on something that is not Unix based, but still it is there. So we want original file, file system path, original path is okay. What we want to do? Okay, let's PNP directory. Okay, so I want this, and then this is the path. The file system path. Symlink path is just link, and then I want to create a symlink. So std file system. Oh, wait, art. Create symlink, original symlink. Okay, so here I should be seeing some sort of new link, and I will call that function here. And I see this test link is created. If I do this on test link, it says that it is pointing to this path, which is the original path here. And obviously I can read directly from here as well. Okay, so this is how we create symlink. Then there is something called this will be basically your soft link. Then there is another thing called hard link. Again, I have no idea whether this will work on Windows or not, because I have no idea whether hard links are supported there, but it is a thing on Linux at least. Original file system hard link equal to hard link. PD file system hard link original hard link. Okay, so we have test link, and if we run it, we should see some other file name hard link. Okay, wait, I forgot to call it here. So I done this. Okay, here I see this called hard link, and if I do hard link, it gives me basically nothing. I can read it and I will get the exact same data here. Okay, so this is how we create a hard link. And by the way, if you don't understand the difference between symlink and hard link, you can Google it. The basic idea is that if you remove the source file, the soft link will break, but hard link will not break because it is not pointing to the file name, it is pointing to the specific inode on the file system. So even though the file system entry corresponding to the file name itself is gone, the inode is still present, and therefore the data will still be accessible. That is basically the summary. But most of the time you will be seeing the symlinks being used, not really the hard link. It is more like that you created sort of a shallow copy of the file where you see the same data in two different places with two different names, but on the disk itself, data is not duplicated. So this is kind of like that. Okay, now we want to check whether some path exists or not. Check if path exists, because many times you will be trying to open a file or write into a file, or you want to probably load some configuration from some location, or you're taking some file path or directory path as input somehow, and you want to test whether it actually exists or not before you try to do something, because you can't really read from a file that does not exist, and you probably don't want to write into a file that already exists many times. So we need some way to check if path exists. So check path exist, and we need some path to check. Path exist. That will be okay. We can check for this path. Similarly, file system path does not exist. Okay. So what we will do, we do something like this. File system test. Oh, it got okay. So we can do the same for this. Does not exist. And we want to check path. Check path exist. It says that this particular path exists and this one does not exist. So this is how we check whether given path itself is valid or not. Then we want to check whether a path is file or directory. Check if path is file or directory, because if you are expecting a file, a directory will not really work. You can't read from a directory or write into one. Similarly, if you are expecting a directory path, a file path will not really work because you can't create a directory in a file or a file in a file. So, void check path file or directory, and as usual, we will have one path. To the file system path is equal to debug remote and system path. File path. We want to check that is a directory or something. Okay. So okay, this 3D file system is directory. Is a directory. Similarly, we can check for file as well. File system is regular file. File path. Yeah, regular file. Okay, check file path file or directory. here it says that this one is a directory and this one is a regular file. Similarly, you can check if path is a symlink. Okay, and before that, what happens if I give it a symlink here? Test link. Okay, it says that it is a regular file. Okay, now I specifically want to check if it is a symlink or not. So void check symlink. Okay, this. The symlink file path. This is a symlink. So path symlink. Okay. It says that this path is a symlink, and now if it is a symlink, basically resolve a symlink. Where does the symlink point to? So I want to read the target. Okay, so if it is a symlink, so I want to read target. What do we state? File system read symlink file path, and then I want to target to target is basically this check path symlink. Okay, so just run it again and see what comes up. So here it says that this path is a symlink and it points to this particular path, and basically this is the same output if you use ls-l, this test link. So this is also reporting the exact same path as the target for this particular symlink. Now suppose we want to convert path from absolute to relative. Okay, so okay, that absolute path from relative path. Okay, any questions so far? Anyone got any questions? Okay, I will take it as a no. So we want to get absolute path. Absolute path. File system path relative equal to test link. Okay, and I want to get the relative path. Absolute path equal to system in absolute relative. Relative path is then a new line we print the absolute path of- okay. So here it says that a relative path is this one, and the corresponding absolute path is basically this one. Okay, now we want to get a relative path. Get relative path from absolute path. Basically, we are going in opposite direction. Avoid relative path. Okay, so here we will start with absolute path equal to we can remove this extra dot. Okay, and we want the relative path in relation to some base path. So base path will be, let us say we want this to be base path. So the relative path will be relative to this particular location. And now I want to get relative path. System relative path equal to the stereo system to path. Okay, so this is absolute path and this is base path. And then we can relative path will be okay. So we can this and we run this again. Uh, oh, okay, it says my relative path. Oh, okay. So this is a symlink. So we are getting the path of the target file relative to this one. So if I change it to say lecture 1 and build it again. Lecture 4. Then for this one, the relative path will be this one, but for that this one, the target was somewhere else here, and the base path was here. So the relative path came out to be go back to one directory and then do this. So this is how we get the relative path. Okay, now we want to check file permissions. Set file permission. So we can take example of file here, file system path, file path equal to x1. Okay, and we want to read the permission. So std file system permissions. The file system status file path dot permissions. So now we want to basically print the permissions. So cd std cout file path. And then we want to basically interpret this part, and we can do that something like this. So missions and std system permission terms owner read. Okay, so this will give us this one. Okay, so we want to compare this so that it is not none. And we want to compare so the file system becomes none. So okay, so if it is okay, so what we can do, we can put it in a little bit simpler way. So if this is the case, we print std out and we print that it is for read. Otherwise, we print blank. Okay, and similarly we do for owner write and owner execute as well. Okay, owner owner right, and similarly owner execute and the okay, so read, write, execute, and then we basically print it by permissions. And here we see that it is read, write, execute all for this one, which is true. Similarly, if I do this for owner others exec or others write, others read, and build it again. And now it will see say that except for owner and group, if we are checking for others, they can read the file, they can execute the file, but they can't really write into this file. So this is how we can check for this one. And if you see here, it has file system, it has others read, write, execute, owner read, write, execute, group read, write, execute. Oh, shit. Let me share my screen again. Wait. Is my screen visible now? Okay, so basically this is how we check for permissions. For getting the permission, we use this status dot permissions, and then we basically interpret individual bits like this, and this will basically contain permissions for owner, group, and others, just like Linux has it here. Okay. So initially it was basically owner read, owner write, and owner execute. So the first output was this RWX. Owner can do anything with this particular file. But for others, it is readable, it is executable, but it is not writable. Okay, and these are exactly the same that we see in the shell output if we do ls-or th, or we do something like a stat on this particular file. Now, this file system forms here, if you see, there are all the permissions put here. So if you want to check for set UID bit, set GID bit, sticky bit, all those are available here. Okay, so others read, write, execute, group read, write, execute, owner read, write, execute, all is basically a shorthand that all three permissions are there. Okay, so set UID, set GID, sticky, these are different permission bits which basically impact the how the file is going to be accessed and how it is going to behave at runtime. So all those bits are available here, and obviously some stuff from this will not really work on platforms which are not basically Unix derivative, right? So all these will work online, all these will work on BSD, on macOS as well, but on Windows, not all of them will work. Okay, probably you will get something for owner, user, and others, but I'm not really sure how this set UID or set GID or sticky bit is going to work on Windows. Most probably you will not really get any meaningful data on that. But again, check the specific documentation for the specific platform you are using. So as I told you in the beginning, many things in the file system are derived from Unix-based operating systems, because that is where most of the stuff in C++ tends to happen. So not everything will be applicable for operating systems which are not really derived from Unix, or not really have any sort of parity with that thing. Okay, so this is how we do this permission stuff. Okay, similarly, we want to say change permission. Okay, we want to change permission for some file. So set file permissions. Okay, and what we will do here, we see that for others it is read and execute, but not write. So what we will do, we will make it writable for everyone. So for that, okay, what I will do, I will change it to get file permissions, and then I will make another file set file permissions. And I want a path. Okay, so this is here, and I want to set the new parameters. So std file system new permissions, std file system terms others read. Okay, so the permissions are ready here, and then I set permissions std file system permissions, and first parameter is path, and then new permissions. Okay, so what I will do, I will set file permission. Okay, so what I am doing, for the same path, I am printing the existing permission first, then modifying it, and then printing the same thing again. So let us see if it works. Okay. So here you see, first it was this, then we specified that others should be able to read, write, and execute. So read and execute was already there, we just slapped right into it. And when we read the permissions again, it is RWA. So this is how we basically set the permission. So this is where this file system part kind of ends. And after this, we basically move to this reading from file and writing into it, from a specific file. So before we pick that topic, anyone got any questions? Can you go up? Just wanted to note it. Go up where? Which line number? File permissions once again. File permission part. Okay, so here is the quick summary. File permissions. There are three parts. Owner is the user who owns the file. Group which gets access to this particular file, and others is basically everyone except the user and the group. Okay, and member users of given all member user of given group get this permission. Okay. Okay, so how does this work? Then there are three permissions. One is can read, one is can write, and third one is can execute. So this will basically control whether you are able to read from the file or not. This one will control whether you are allowed to, or whether you will be able to write into the file. And third one basically controls whether you are whether you will be able to execute that particular file or not. Okay. So if I set the file permission in a way where I say that the owner is going to be able to read, write, and execute, but the group I am specifying as owner is only going to be able to read and execute, and for others it is going to be only read and execute, or maybe none of that. Okay, so what happens that the particular user that I have specified here. Okay, okay, so this is user basically. So that particular user will be able to modify the file, but no one else will be able to modify the file, but they will be able to execute it. So when you install a bunch of tools in your Linux system, the binaries are configured in the way here anyone can read and execute. So for example, if I say which ls and I do ls-lrth, user bin ls. So here, what do you see? You see owner is root, group is root. The owner gets RWX, can read, can write, can execute. If it can't write, you can't really replace this binary by doing say apt update, apt upgrade, or some other stuff, right? That should be possible. So the user itself should be able to write into the file. But for others, they don't need to write into this file. They only need to be able to execute it and read from it. Without reading, you can't really execute. Okay, so the group and the others are given Rx permission. They can read from the file because without reading they can't execute, and when they are reading it, they are explicitly allowed to execute this binary as a process. So this is basically how this works. And then there are some extra bits like set UID, which basically says that doesn't matter which particular user is trying to start this binary as a process, you always start with this particular user instead of whatever user is currently active as or basically is trying to start the process. So that is how things like ping work. You want to use ping without root, but ping requires ICMP traffic. It has to open raw socket, which is privilege operation that can only happen via root. So ping is given ownership of root, and the set UID bit is set on ping. So if you do something like this, right? Okay, ping is not set. Okay, yeah, on sudo see it is set this set UID bit. So this basically what it does, it will make sudo always run as root, because only then it will be able to change permissions arbitrarily from one user to other one. So this is how these things work. If you want, I will probably find some much detailed write-up about the permissions and how they are supposed to work, how they exactly work, the difference between them and all that stuff. But I hope you get the basic idea of permissions. Okay, any more questions? Wanted to understand the code part. So setting the permission or getting the permission, which one? So for getting the permission, you read the permission. So basically some numeric alternative of this weird looking string, and then you basically uh, figure out specific places. So what I am doing here, this is basically bitwise operation. So if you remember in earlier lectures, we talked about those bitwise operations where you can use and or. And the basic premise is that you will be able to figure out the specific bit. Okay. So what exactly here is happening that in the permission, there are different bits denoting different things. Okay. And we want to figure out those specific bits. If that bit is that particular bit is one, we have the corresponding permission. If that bit is zero, we don't have that corresponding permission. Okay. So what we are doing here, we are taking basically one bit at a time, as in one permission at a time. Then we are doing a bitwise AND. So what happens that all other bits become zero, and the bit pertaining to this specific permission, that will either become zero if we don't have the permission. So that means that this basically comes out to this, okay, or it is one. In that case, it is not equal to this. So if it is not equal to this non-permission part, that means that we have the permission we are checking for. And exactly same thing we are doing here and here. And in the setting permission part, we are doing the opposite. Instead of checking for specific bits, we want to set specific bits to one. So instead of doing bitwise AND, we are doing bitwise OR. And what it will do, it will basically leave other bits unimpacted, and it will only change the specific bits for the specific permissions that I have specified. Only those bits will be set to one, and the rest of the bits will be left as it is. There won't be any change because one or zero is one, but one and zero is not one, it is zero. So that is what is happening here, and that is one of the biggest or rather most common use of bitwise operations. Okay. So now we come to this file reading part. And file IO. Okay, so we remove this. And now what we want to do, we want to write into a file. So for that, we need this fstream part. Okay, so for file system, you need std file system, and for file IO, you need std fstream. Okay, so we have already included here. Okay, so void write into file and std stream output file, and we specify file path here. So okay, so we can specify output.txt here. Okay, and so we can check if file is open or not. Not output file, we can say that could not open file, and if that is the case, we can basically return from here. Otherwise, what we will do, we have this one. Okay, so just like we are doing this thing here, this angle bracket stuff, we can do the same thing here. Okay, so this is text. Similarly, we can do this is more text. Okay, and we can keep doing this. This is even more text. Okay, and then we can close the file. So this is how we are opening it. We are just doing a sanity check whether the file was actually opened or not, and then we are basically closing it. So if I run this file, okay, it says could not open file, but touch output.txt. Okay, so here basically it is going to open the file only if it is already present. Okay, and we don't really want that. So it is food. Okay, so there are two things. One, the file was not created here, and second, that even if we run this again, this data is not getting repeated because it is basically overwriting it. Okay, so what we will do, we do not want to overwrite, we want to append. So for that, what we will do, std ios, we will do append. Okay, and now it is appending. Okay, so now it is written once, we do this, it is written twice, we do this again, it is written once again. So now here what happens that the syntax is something like this. So you specify the file name and then you specify the mode. Okay, and the mode can be bitwise or of multiple things. And for example, that will be iOS in, it will be iOS out, it will be append, it will be truncate. Is there something else as well? Yes. In, out, append, truncate, and iOS binary. Okay, and iOS binary. So what it does, opens file for reading. This opens file for writing. Is create if file does not exist. Append if file exists. If file contains data, nuke that data and overwrite. And okay, so this is bind useful when writing binary data into file where we don't really want any sort of funny conversion happening. So this is useful only in that case. Otherwise, by default, we will generally be using mostly files which are text. So this binary part is useful when it is not really a text data. For example, if you are reading from a image file or audio file or video file, or probably you are writing into a image file or audio video file or something like that, or maybe a compressed data or some encrypted data, whatever. Okay, so in those cases, you will basically open the file in binary mode and you will be basically dealing with binary blocks. You will be reading in a generic buffer and you will be writing a very generic buffer. Okay, now we can specify all this and we can specify a combination of this. Now there are a couple of more things. There is f stream, there is if stream, and there is off stream. Okay, so this is basically if stream, it can do both. Only for reading and only for writing. So if you are only writing into a file and you don't really have to read from the same file at same time, so you instead of using f stream, you can probably use off stream. Now the question will be that why not use f stream and be done with it? So one very obvious answer is that if you use off stream and if you accidentally try to write into it, it will not really work. Okay, if you used f stream and you accidentally write into it, the data will be written. But then you can ask that, okay, while dealing with f stream, I can specify that it is only for reading or writing, or maybe I specify that it is only for reading and I don't really want to write. Yes, you can do, but then that is one extra thing that you have to take care of. And if you forget that for whatever reason, down the line, bad things can happen purely by mistake. So as a safety net, you can resort to using either this if stream or off stream, depending upon your use case. And if you have some case where you will be reading from the same file and writing into the same file at different places, then for that use case, F stream is going to work just fine. Okay, now I hope you notice that there is something funny here. And the funny is that these two have basically identical syntax. And this is because both of these are basically a generic streams. So C++ has a concept of generic streams, which are then extended into a bunch of different things. So you will see input stream, output stream, you will see string stream, you will see file stream. And then the good thing is that this syntax works with the stream. And since it works with the stream, it will basically work with pretty much any type of stream. That also means that if you are doing some sort of generic input output, instead of taking file parameters or these file objects in parameters or taking paths, you can also write your code where you accept a very generic stream and you say that, okay, as long as it is a valid stream where I can do these operations, I don't really care about what is happening behind this particular stream. And the good thing will be that then your code can be used with a file. It can be used with a interactive output, that interactive console. It can also be used with a string stream, and someone else can come along and say that, hey, I will convert this generic stream and I will slap some network part into it. So if you squint your eyes and pretend that this is a stream and push some data into the stream, it will magically pop out on other side of internet. And your code will work with that thing perfectly fine, even though at time of writing the code, you had no idea about how to deal with network. And even at that stage, code has absolutely no understanding and no notion of network, socket, and all that stuff. It is still going to work. So this is a very basic idea of how to write into a file. It is pretty straightforward actually. And then we will do the opposite thing. We want to read from file. File, void, read from file. And for that, what I will do, I will, okay. Make file, okay. So for that, we again open the file. Stream input file and it is okay. And if it is not valid, we don't really want to read and we can return it. Okay. Now what I want to do here, we want to read this file line by line. Okay. So I will declare a variable here and then basically I want to read from it. So since I have no idea how many times I am going to read, I will basically use get line. I am reading from input file and I am going to read into this line. And this will basically read one line for me and it will print it here. So I can just print here and okay, let us see how that works. Okay, terminal, and we do this. Oh, wait. I didn't even call this function. Read from file. If I run it, that entire make file is getting printed here because I am reading and printing each line at a time. Okay. Now, this basically assumes that our file has multiple lines, or rather our data is split across some rather nice lines, and every line is basically usable on its own, as in your data is not magically split across a line, or same line doesn't have some other half-baked stuff. At times, there will be cases where this is not really true. Okay, so maybe your data is split across different lines, or maybe your data uh, is you have to do some other stuff with that. So where basically your line by line stuff is either getting problematic or it is kind of less than ideal state. So in that case, what we can do, we can also try to read whole file in one shot in one large buffer, and then we can basically process that string stuff as we see fit. Maybe we want to tokenize it using Boost. Maybe we want to split it across some other separator or bunch of different other separators, whatever. And those separators may or may not be new line, right? So if you want to do that sort of stuff, and your file is rather small, okay, so you can also try to read entire file in memory in one shot and then deal with that entirely within memory. And this is something that you see is a rather common way of doing things in some other programming languages. So we can do the same thing here as well. Oh wait, I forgot to close the file here. File dot close. Okay. Fine. Read entire file, and for that I will do kind of the same thing here. Okay, and instead of doing right this line by line, what I will do, I can take a string buffer. Okay, so for that I will need a header, this string, and then here in this code I can create a string and the data, and then in this string I told you this is yet another string, so this string related input output will keep working on it, and the file is this one. So dot read buffer, and I put this entire thing here, and I want to print this str. Oh, okay. So basically this is a stream, and from a stream we are getting that final data in string and then printing it. Okay, so then we can do read entire file. Okay, so it is run, and here it is printing the same thing again. Okay, so we did these two parts. Now, again, there will be cases where both of these conditions will not really be true, as in that line by line read is not going to work for you for whatever reason, and file is not small enough to pull the system where you can read entire file in one shot. Okay, so for example, you are dealing with a huge CSV or huge JSON, and if you try to do that, it is not going to work because your CSV is rather huge, sitting at size of 2.5 GB. So if you try to load that and then you try to split it across some separator, you will basically end up eating huge chunk of memory. And if your system does not really have crap ton of memory, you will be basically terminated. The process will be killed because it eventually will run out of memory. So in those cases, you can't really read entire file. So what you do something like a middle ground. So instead of reading in one shot, what you do? You create a small buffer and you read the file in smaller chunks, okay? And then you process the chunks in memory at runtime. So, for example, you can use this thing to basically, in cases where your data can be streamed, as in you don't really need the entire file to make sense of it, you can make sense of it in chunks and pieces. For example, if you are dealing with JSON, so in chunks and pieces, you will at least know that, okay, here my next key is getting started. This is where my string starts. This is where the string is ending. So you go back and see that, okay, which was the string that started, that sort of stuff. So that will require a lot of other stuff. But the idea is that you will be able to handle rather huge files without going out of memory every single time. So for that, we can do something like this. So read from file, the entire file, void read file in chunks. And we do the same thing here. Okay. And then what we do, we can create a buffer and we want buffer, so we can create a vector. Okay. And okay, what is the size of this make file? This is 9 KB. So what I will do, I will create buffer to store chunk of file. To the vector, I will create a vector of characters. Buffer, and I want it to be of this size. So basically what I am doing, I am specifying the size here and the initial value. So entire buffer will be 0. And this buffer will be allocated to have at least 1024 characters in one shot. Definitely we can extend it, but instead of extending it every now and then, I can just specify the minimum size at time of initialization itself, and then we can later change the size anyway. So we can, we have the buffer here, and then what we can do, we can again loop And since we don't know how many times we have to loop, we can check for end of file. Read until end of file is reached. And then what we will do, we can do input file dot read function and then buffer dot data and then buffer dot size. Okay, so input file and then we can do std cout chunk. We can keep counting chunks as well just for fun. So unsigned count chunk equal to 1. Std and real, and then std cout. Okay, so we can do this. And read file in chunks. And we can run this again. But oh, wait, what? I missed this negation. Okay, build this again. Okay, so here it says prints again. And okay, here you see this chunk one. Oh, wait. I forgot to increase the counter. So wait, we will get to know in how many chunks this file has been read. So this is printing just fine. And I get for chunk. Okay, here you see that it has read the file in total 10 chunks. Okay, and we still get pretty much entire data. Just instead of reading it in one shot, we are reading it in some chunk size, and then we are doing some processing on it. Okay, any questions so far? Once we know all these concepts, how much should we rate ourselves on a scale of 0 to 10? Wrong question, buddy. I think only inventor of the language himself would be able to rate himself somewhere around 8 or 9 out of 10. And people who are writing compiler for C++ will be giving him pretty close competition for that 8 or 9 out of 10 rating. For myself, I rate myself in C++ somewhere around 2 to 3 barely. Okay, and then you can basically extrapolate. And the reason is that C++ is not one language. It is basically a khichdi of 10 different languages trying to fiddle with each other. So I am covering only those parts which are going to be more useful for your regular life, because most of you won't writing V compilers and you won't writing V kernels or some hefty frameworks or doing some very intensive optimization sort of things. Okay. As far as that malware class is concerned, once you go this entire series and you do little bit of practice, most of the stuff from malware series will be pretty much straightforward, because then the implementation will be basically like 90% of this stuff will be like, okay, yeah, this makes sense. The 10% part will be how to think like an offensive guy, how to think like an attacker, and how to figure out a specific technique. Okay. -10 came from -10. Come on, man. This is a weird language. I told you. Other languages are not insane. Basically, there are only two languages which are kind of insane. One is JavaScript, other one is C++. The joke goes that JavaScript is lingua moronica because its syntax is pretty moronic. There are a lot of nonsensical things which don't really make sense to any sane person. And the C++ is called lingua satanica. It is said that Satan himself sat somewhere in the deep corner of hell and invented this language for us poor plebs to suffer. So here we are trying to suffer together. Anyway, any questions in this basic file read write process? Okay, fair enough. Now, all this is fine on surface level, but then when you are reading a file, you are probably trying to process that data some way, okay? And most of the time, the data will be in some easy to process format, okay? Maybe it is XML, maybe it is a bunch of HTML pages that you are trying to parse and extract some data out of it. Maybe it is JSON, maybe it is CSV, whatever, okay? So in those cases, instead of reading this and doing all that stuff on your own, most of the time you will use some external library. Okay, so if you, for example, say you want to deal with CSV or JSON or some other rather common format, most of the libraries will do this reading part or even writing part to some extent on their own. You only have to either specify a file path or you open the file and pass them that particular file object or file descriptor or something like that. And the reading writing part will be taken care of by that particular library. So you don't have to think about these nitty-gritties in case you are using some sort of library like that. Now there will be libraries which will not really do this for you, or maybe they will only read for you, but they will not really write for you or whatever. But so in those cases, ability to read write on your own still comes handy, or maybe you are trying to deal with some file format which does not really have very good support of libraries. Maybe it is some very niche format, or maybe it is something that is internal to your project or your company or your group, whatever. So in those cases, these abilities will come really, really handy. Okay. Now, since we know this, how to read this, and we want to do something with data, what we want to do here, we want to how to process CSV. Okay. And the reason why I am taking example of CSV is specifically because if you are uh, someone who deals with security side of things, CSV happens to be very common format to export data or import data. Okay, there will be tools where you can filter some data and they will give you option to export and download the data either in Excel format or in CSV format or in JSON format. But CSV seems to be much easier than JSON. So we are starting with CSV. Okay. Similarly, if you are someone who deals with malware analysis and you are someone who tries to keep up with newer samples which are coming in the wild, you probably also subscribe to some sort of threat feed. Maybe it is from Malpedia, Malware Bazaar, Virus Total, some other stuff. And most of them will give you that data in a nice structured CSV format. Okay, they will say that, okay, every single day, once in 24 hours, you can hit this endpoint, you will get a CSV. It has these many fields. Now do whatever the hell you want to do with that. Okay, now if you have that CSV, obviously you can load that in Excel or some equivalent tool and do some sort of semi-automated filtering. But again, we are not really going to do that. Also, that is not really scalable because if you want to automate that, automating Excel is going to be pretty much pain, and that will also require you to run Windows. That will also require you to have some extra licenses. So if it is CSV, that is plain text, why bother with Windows or Excel or deal with all that pain of automating that stuff? And you can read the file, process the CSV, state in C++, and be done with it. And then you can run it on your laptop, on Linux, BSD machine, whatever. So for that, what I will do, wait, where is that library? Okay, so there is this really nice library. Wait, let me find the link. Okay, so here is the link. I am putting this on chat. This is the CSV parser, okay, that we are going to use. There are many other libraries, so if you want to use some other library, it is entirely fine. No big deal, just that we will be using this. And we will be using CSV from Malware Bazaar. So let me find that link. Okay, so if you want to download this CSV parser, there is this direct link as well. So that is only one header file. Everything is within that single header file. So you only have to copy that, include with your project, and it will be done. Now you also need malware bazaar CSV. So let me find that link. So here is malware bazaar. Link is in chat. And if you go to the page, you will see access data, API export, that sort of stuff. A screenshot is put on chat. Okay, and now if you go to export, you will see option like this. Okay, so the top option is CSV file. So that is the file that I am using with some modifications because this CSV comes with some commented lines, and since CSV does not really have comments, so different libraries will try to deal with that differently. So for sake of keeping it easy, I have removed all those lines from this CSV at my own end. So you can download, you can remove those commented lines, and then you can use the same CSV for the exercise. Now I want to copy that header file here. So what I will do, I will just copy the CSV file here. Okay, where's the path? Wait, what project is this? Automating with C++. So automating with C++, lecture 4. And this is this one. Okay. AP, CSV, some CSV. Okay, so the header file is copied. So here you see this is the header file. So I have copied this here. And I also want to I want to add different library here, different executable here. So add executable. or rather leave it. I will do it in lecture 4 itself, and I will leave these functions as it is, no big deal. So what I will do, I will include the header Vincent CSV that CSV is included here, and I will do something like process CSV. Okay. But so what I want to do, if I open the CSV, okay, let me copy the CSV as well. CSV, CSV. So, okay, so, okay, CD lecture 4. Here's the CSV. So if I open this like this, you see some lines here, and here the first one is basically your column header. Okay. So it has a timestamp when the sample was first seen. It has hashes in SHA-256, MD5, SHA-1, reporter file name, yada 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 yada. So a bunch of different things. So the first step is to basically okay, open this and try to read some columns. So what I will do, I will use this library and I want, okay, where is the code? Okay, so CSV format. So basically I want the blank spaces and tabs to be trimmed. So instead of doing it on my own, since this library can do that stuff for me, so I'm just asking it nicely to do that stuff for me. And then I need CSV reader, CSV reader, and I need to specify the file name. And format. Let me see if it is copy. Okay. Okay. CSV. Fine. So I will copy this path here because I want it to work on the remote server. So this is done. And then I want to read it row by row. So let me count total number of lines. Unsigned in count equal to 0 and plus count just for a sanity check. And std cout entries again red. Okay, so just a quick sanity check basically. And if this works properly, we will read individual columns. Terminal. Okay, lecture 4. It says 693 entries have been read, so at least this reading row by row is working. So since it is working here, we can read some specific columns. No, that means, okay, so what are the stuff that I want to read? I want to, okay, let us say that I want to read this SHA-256 hash. So that will be row, and we can specify column like this, and then I want to get it as a string. So I can specify the format in which I want. And okay, right now let us see. It should work. So it prints all those hashes. Okay. So hash is printed. What else we can print? We can print file name, file type with file name. Yeah, file name and file type. Fine. So we are getting this. Okay, so what we can do here? We can print here file. Wait, what was the column? So file name is row, column name is file underscore name, and we can get it as a string. And we can get the file type. So it is file type this get std string. Okay, and then end of the line. Fine. This should print all of this. Okay, so I go back here into clear. F4. So here it prints hashes, it prints file name, it prints file type. Good enough. So generally this is how you try to parse CSV, and now since we are able to read it row by row, either we can store it somewhere or maybe we can perform some extra checks. For example, let me copy some specific hash. Okay, and I copy this hash and I want to search for some specific hash. Okay, so I want the string hash to be searched. Okay. Okay. Now what I want, okay, you can remove this bound reader. You don't care about it. You can remove this as well. No need to care about it either. What we want to do, we want to do search for this hash. Okay. And okay, so what we can do, we can copy this std string hash equal to this. We can remove with this one, and we want to check hair state or find hair first. Not equal to std string. We can remove all this and put it here. Okay, so we build this again. Wait, what? Mm, build. Okay, so we are searching for some specific hash. The hash is found. This is the data. And if we want some more columns, we can probably check for other fields as well. So for example, I can check for Miami type. And the column name is Miami type dot get std string, and probably I also want to check for this 80% or something else. Okay, so I want 80%. 80%. Let us dump it as a string itself right now and see what sort of data we get. And run it again. Okay, so it says name is this, type is this, MIME type is this, VT% is 6.94. So this is how we can extract specific columns. Okay, and either we can go row by row, or we can probably search for some specific column. So this is generally how we read the CSV part. Okay. Similarly, for JSON, there are other libraries where we can use them to read JSON and extract keys and values, or possibly modify them. Okay. So for today, the session will basically end here. Today was a little bit longer because last session did not happen. In next session, we will cover a little bit of JSON parsing from reading. I think we will try to read a JSON file and see what we can do with it. It is going to be a little bit more involved because JSON has a lot more things. It has simple arrays, arrays of objects, that sort of stuff. So it is going to be a little bit more involved. So we will do this in next session, and then we will move on to structure classes, little bit of object-oriented programming, and some other related concepts. Okay, any questions? बहुत ज्यादा हो गया भाई. It is still kind of okay. I did not want to delay. I don't really want to stretch this series for way too long, and I missed a session last week. I wanted to cover up. So some stuff is covered today. Some stuff will be covered in next session. Okay, anyone got any questions for this? Okay, fine. So I will take it as no one has any questions. So what I will do, I will copy the code, the notes, both in uh, Discord channel, and then I will also put some possibly practice problems. And oh yeah, I will put some practice problems for this file IO stuff at least. So do that. Okay. If you get stuck, drop your questions. I will take a look at them and see how quickly I can help you out, and then we will move on to some more things. Okay. Thank you, everyone. Thank you for giving your time. See you on 15th, same time.